All right, here we are, taking a look at example 3, where we're asked to integrate the function x over the region W, which is bounded by two surfaces, z equals 4 minus x squared minus y squared, and below by z equals x squared plus 3y squared in the first octant. So the first octant is the region where x, y, and z are all non-negative, sort of like the three-dimensional analog of the first quadrant. So the first octant also contains the first quadrant. So what I would do here is first figure out where do the two surfaces intersect. Because for all of these, we need to know which surface is above the other in some sense, either in the x direction, y direction, or in the z direction. More commonly than not, we're going to be in the z direction. So why would we think the z direction besides the fact that the last couple examples have been that way? Well, we would think of it because these equations were presented to us as being solved for z. So because each of these equations are functions of x and y, that means they must pass the vertical line test. In other words, if you were to stab this imaginary rod in the z direction and poke these surfaces, no matter where you poke the surface, it would only strike once. So this is a really good clue that we should try to interpret this three-dimensional region W as a z-simple region. It's because each of these are presented or solved for z a function of x and y. So they necessarily pass that test. When things aren't solved for one of the variables, then things can get a little bit more interesting. So what I would do here is check where do they intersect. So where do the surfaces intersect? Well, two surfaces, they intersect when they're equal. So we can just set their equations equal to one another. When we do that, we can go ahead and, well, it seems best to collect the squared terms and then simplify to see what we have at this stage before we go any further. From earlier and from earlier in this course and even before this course, you should be able to recognize that this is an ellipse. So this is an ellipse in the xy plane. So let's go ahead and sketch that in the xy plane. The easiest way to sketch an ellipse in the xy plane is to sketch its x and y intercepts. So when y is 0, this whole term is gone, so that we just have x squared equals 2. So this means x equals plus or minus root 2. And for our y-intercepts, we'll find those by setting x equal to 0. And in a similar fashion, this term is gone. So then we have something that is divisible by 2. Divide each side by 2. So then we'd have y squared equals 1, which would give us y equals plus or minus 1. Now we're in the first octant, which means in the xy plane we're in the first quadrant, so we don't care about the negative roots of either of these. We just want the positive root 2 and positive 1. So we'll go ahead and sketch these now in the xy plane. First quadrant. The square root of 2 is a little bit bigger than 1, so we know that this ellipse must be elongated in the x direction. So we should have something something like that. So there's our root 2, there's our 1. Now, for a moment, I'm going to go ahead and just kind of like imaginarily draw this other side here. So what we know is when we're on the ellipse, this tells us that the one surface, I'll just call it Z1, the one of the surfaces, must be equal to Z2 on when we're on the ellipse, so if we plug in values of x and y on the ellipse, we have to get those two are equal. If we plug in a point within the ellipse, one of them is bigger than the other, so let's just say it's this. And then if we plug in a point out here, the only thing that could potentially happen here is that they flip. There are, technically you could get something where like they just touch for a moment and they go back the same way they were, but we're not going to worry about that. So really what we want to do here is all of this region out here, this is not in the first quadrant, and therefore it's not in the first octant, so we don't care about any of this region here. So we can just go ahead and delete all of this, not worry about that. So what we really want to know is, in this region here, which surface is bigger than the other? Well, let's go ahead and just pick the point 0, 0 to plug in as a test point. So, as a test point, we can take x squared plus 2, oops, is it 3? It's 3. X squared plus 3y squared, plug in the origin. That's going to give us 0. And clearly, 0 is less than what we get when we take 4 minus x squared minus y squared and plug in the origin, because we get 4. 4 is definitely greater than 0. So this implies that for no matter what xy point we pick in our region D, so let's go ahead and say that our region D is the interior of the ellipse, but the portion of that interior that is safely within the first quadrant. So right there is D. So if we take any point within our region, x comma y, and we plug it into each of those equations of the two bounding surfaces, we will always find that the z value must be bounded below by the lower surface and bounded above by the upper surface. So, what we now know is that our triple integral over w of x dv, this must be equal to the double integral over d of the single integral from x squared plus 3y squared to 4 minus x squared minus y squared x dz dA. So we basically just figured out the inside integral. Now that we have it set up like this, we have a couple options. We now need to figure out how to describe D. Or a lot of times I'll say the word interpret. How do we describe or interpret the domain D? Well, the one way to do it is by saying vertically simple. Because if we strike no matter where we strike a vertical line through our region, we're always hitting this on top and this on the bottom. So therefore, for vertically simple, every x value is between 0 and square root of 2, and every y value is between 0 and, well, we'd have to solve this equation of the ellipse. We'd have to solve this for y. Solving this equation for y is plus or minus the square root of of, let's see here, this would be 2 minus x squared over 2. So this would be the square root of 2 minus x squared over 2. We don't have to worry about plus or minus. We only have to worry about plus because we're in the first quadrant. Now our region is also horizontally simple because no matter what horizontal line we strike, it hits this on the left and this surface on the right. So in which case, each y value for a horizontally simple region is bounded below by 0 and above by 1. The x values are bounded below by the boundary curve x equals 0 and bounded above by the boundary curve. Well, we'd have to yet again go back to the equation of the ellipse and solve this equation for x. In this case, x would equal plus or minus the square root of 2 minus 2y squared. And we don't care about the plus or minus because we're in the first quadrant, so we know we're going to take the plus. So this would be the square root of 2 minus 2y squared. So far, it looks like horizontally simple might be the best. So let's see. There is a third option we can do here, and this would be to interpret the region as radially simple. So for a radially simple region, we would say theta is bounded between, well, in this case, if we look up at our region, we start off at an angle of 0, and as we increase this angle, right, it is radially simple, because no matter what ray I strike through my region, it always, on the outside, hits this boundary curve, and on the inside, the last thing it hits is the origin itself. So theta goes from 0 to 2 pi, a right angle, and then r goes from this dot, which is r equals 0, to whatever r is on this curve. So 0 to pi over 2, and then r would be between 0 and whatever r is equal to. So x squared plus 2y squared equals 2. Well, we can just plug in what we know about polar. In polar coordinates, x squared is r squared cosine squared theta plus 2 times r squared sine squared theta equals 2. Well, what do we have here? We somehow need to solve this equation for r squared. So we can factor out an r squared, in which case we're left over with cosine squared theta plus 2 sine squared theta equals 2. And we can actually solve this because, let's see here, this is a 2, not a 0. If this were a 0, then we could just say this equals 0. So to solve for r squared, you actually have to divide both sides by this quantity. Ooh, so then we have r equals plus or minus square root of 2 over, oh boy, that is just a mess. So solving it that way is not going to be great. There is a way you can solve this. There is a way you can solve this. It's not going to be that great. I do think at this stage, probably without going into a long algebraic excursion, horizontally simple, I think, is going to be the easiest here. I do think that's going to be the easiest. All right, So in this case, if we choose horizontally simple and abandon the radially simple because it looks like a nightmare, it's not that you can't do it, but that's a little bit beyond the scope of this video. You'd set this up as the following. If we choose horizontally simple, that's the winner, then this would be 0 to 1, integral 0 to the square root of 2 minus 2y squared, integral x squared plus 3y squared, 4 minus x squared minus y squared, x dz dx dy. And that is the integral fully set up. And then if you want to see the subsequent steps for how to work the integral, my completed notes are online. For these triple integrals, the focus is definitely setting up the triple integral, not so much the evaluations that go from there. If you go through all the steps, you get 16 15ths as the final answer.